This video is going to be about the Bose-Einstein integral. So the integral is given by the integral from 0 to infinity of x to the s minus 1 over e to the x minus 1 dx. So to start off, this integral is a definite integral, but the solution is not going to be a constant because the integrand here is in terms of s. So the best we can hope is to have some function in terms of s. So to start off, I can rewrite the integrand in a different form. So we have the integral from 0 to infinity of x to the s minus 1 over e to the x multiplied by 1 over 1 minus e to the negative x dx. So the reason I did this is because this fraction has a well-known solution or a well-known summation. It's 1 plus 1 plus u squared and so on, if and only if the absolute value of u will be less than 1. So our u is e to the negative x, and the absolute value of e to the negative x is less than 1, since 1 all over e to the x will always be less than 1. We can imagine inputting any value for it and we'll get that. So 1 all over 1 minus e to the negative x is 1 plus e to the negative x plus e to the negative x squared and so on. And that can be written in summation notation as a sum from k equals 0 to infinity of e to the negative x to the k. So putting that back into the integral, we have the following: k equals 0 to infinity of e to the negative x to the k dx. Now, in the integral, the denominator e to the x can be put inside of this sum. So I'll do just that. So we have the integral from 0 to infinity of x to the s minus 1 times the sum from k equals 0 to infinity of e to the minus x to the k over e to the x. And that is equal, so just this is equal to e to the x to the minus k all over e to the x, which is simply e to the x to the minus k minus 1. And I can rewrite that in a much nicer, cleaner way. So I'll do just that. So the sum is now e to the minus k plus 1 times x dx. Now this looks a lot nicer, but one thing we can notice is this sum, both the functions in the integrals are both continuous functions, so we can therefore take the sum outside the integral and rewrite what we have. It's k plus 1 times x dx. And now we have our function in terms of x, but it's not really helpful. There's not much we can do from here. So there's not much we can do from here with x as a variable. So we can use u substitution. We say x equals to, sorry, not x, u equals to k plus 1 times x, because then doing that we can get a nicer form. So therefore x equals to u all over k plus 1, which implies that dx equals to 1 over k plus 1 du. So I can put that back into everything I have. So we have the sum from k equals 0 to infinity times the integral from 0 to infinity of x to the s minus 1. But we just saw that x is u all over k plus 1. So I'll rewrite that as u all over k plus 1 to the s minus 1 times e to the negative u, and dx is 1 all over k plus 1 du. So from here, we again have the sum from k equals 0 to infinity times this integral. But we can notice that this term is equivalent to u to the s minus 1 times 1 all over k plus 1 to the s minus 1. And we also see that this is all being multiplied by 1 all over k plus 1. So that is simply just going to be 1 all over k plus 1 all to the s. And then that's multiplied by e to the negative u du. So now we have the sum from k equals 0 to infinity of the integral from 0 to infinity of u to the s minus 1 times 1 all over k plus 1 to the s times e to the minus u du. And since the integral is in terms of u, and 1 over k plus 1 all to the s is simply not in terms of u, it being evaluated at any number for k and s, that's just going to be a constant. So we can take it out of the integral. So we can now rewrite the sum as a sum from k equals 0 to infinity times 1 plus k plus 1 all to the s multiplied by the integral from 0 to infinity of u to the s minus 1 times e to the minus u du. And both these solutions, both the sum and the integral have very well-known forms and there's no solutions. Yeah, both the integrals have pretty well-known forms. So the first sum is simply 1 plus a half to the s plus 1 over 3 to the s, 1 over 4 to the s, and so on. And that is simply just the zeta function. So that is equal to, do I remember how to draw the zeta function? And then the second integral is just simply the gamma function. So that is equal to times gamma of s. Or if we want, we can also rewrite it as this times s minus 1 factorial. But I think this form looks a lot nicer, so let's just leave it as that. Okay, thank you.